Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on solutions, and we've made it to the third objective. Now to start this section, I want to review over net ionic equations. So one useful way to represent a reaction that's occurring in aqueous solution is by writing the net ionic equation. And to illustrate how we go about getting the net ionic equation, we have three main steps. First, we want to write the molecular equation, then the total ionic equation, and then finally the net ionic equation. What do each of these steps entail? This is best understood through an example. So we're going to look at the reaction between silver nitrate and sodium chloride. Now the first step is to write the molecular equation. In the molecular equation, all of the reactants and all of the products are shown in their neutral undissociated form. So for this reaction, we have silver nitrate reacting with sodium chloride to give us silver chloride and sodium nitrate. Then the second step is to write the total ionic equation. In the total ionic equation, all of the strong electrolytes are written as dissociated ions since that is the way they actually exist. Here it's going to be really important to remember our solubility rules. Silver nitrate, sodium chloride, and sodium nitrate. These are all strong electrolytes, so we write them as dissociated ions like we see here. Silver chloride, however, is not a strong electrolyte, so we will not write it in its dissociated form. It stays as is in the complete or total ionic equation. Now, once we have the total ionic equation, we're going to remove the spectator ions, and that's going to give us the net ionic equation. Spectator ions are ions that appear on both sides of the equation completely unchanged. So looking at our total ionic equation, we notice that nitrate and sodium appear on both the reactant side and on the product side. So these are spectator ions that we can get rid of. And once we do, what we're left with is our net ionic equation. So our net ionic equation is silver cations plus chloride anions give rise to silver chloride. Now, net ionic equations are very useful for three reasons. First, by removing all of the non-reacting spectator ions, net ionic equations show which species are actually reacting. Second, net ionic equations help us see the driving force of a reaction, what is really causing the reaction to occur. And third, net ionic equations allow us to recognize the similarities among a large number of aqueous solutions involving electrolytes. Now, the net ionic equation for the reaction between silver nitrate and sodium chloride results in the formation of insoluble silver chloride. This reaction introduces us to a really important topic in chemistry, and that topic is sparingly soluble salts and their solubility. So let's go ahead and talk about that a little more. Most solubility problems on the MCAT deal with these salts, these sparingly soluble salts, which are ionic compounds that have very low solubility in aqueous solutions. Now, understanding this equilibrium allows us to apply the law of mass action to write the solubility product constant, also known as the KSP. Now, for a saturated solution of an ionic compound with the formula AMBN, the dissociation of such a solute in solution can be represented in this way. So when AMBN dissolves in water, it dissociates into its constituent ions. So the compound AMBN, it breaks apart into M cations A with a charge of N plus, and N ions of anion B with a charge of M minus. Now, the equilibrium constant for its solubility, known as KSP, it can be expressed in this way right here. Remember, for equilibrium constants, it is the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. And remember, we do not include liquids or solids. And so the KSP for this reaction, AMBN, is the concentration of the cation A raised to its stoichiometric coefficient of M, multiplied by the concentration of the anion B raised to its stoichiometric coefficient N. Notice how AMBN is not included, and that is because it's a solid, and we do not include solids in our equilibrium constant expressions. Now for silver chloride, we can go ahead and write the KSP for that reaction. It's going to be equal to the concentration of silver cations raised to its stoichiometric coefficient multiplied by the concentration of chloride anions raised to its stoichiometric coefficient. Now, similar to KSP, other equilibrium constants that we've seen like KEQ and KF, as well as equilibrium constants we're going to see like Ka and Kb, they follow the same fundamental principles. They just apply to different types of reactions. So KEQ, this is the equilibrium constant for general chemical reactions. Ka and Kb, we're going to see these are the equilibrium constants for acid dissociation and base dissociation, respectively. And Kf is the equilibrium constant for the formation of complex ions. Understanding when to use each constant depends on the specific reaction that you're analyzing. For solubility problems, KSP is used to describe the solubility of sparingly soluble salts in water. Importantly, the form of the equilibrium constant expression that remains consistent across different types of reactions. It's always concentration of products raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients, excluding solids and liquids. Now, something else we want to further explore is specifically KSP versus KF. So the solubility product constant versus the equilibrium constant for the formation of complex ions. Now, the formation constant, Kf, this measures the stability of a complex ion that's formed between a metal ion and ligands in a solution. It represents the equilibrium constant for the formation of the complex from its ions. So simply put, it indicates how strongly the complex forms and stays together in solution. A higher Kf means a more stable complex. Now, when you're forming a complex ion, this is where it becomes important to distinguish between KSP and KF. KSP is the equilibrium constant for the solubility of the original compound in the solution, while Kf is the constant for the formation of the complex ion from its ions. Now, the original compound's dissolution, that's described by KSP, and the formation of the complex ion in solution, that's described by KF. It's really important to be able to distinguish these two. Now, moving along with KSP, as a solute dissolves in the solvent, the system approaches saturation. So at this point, no more solute can dissolve, and any excess will actually precipitate out. Now, to determine the state of the solution relative to saturation, we calculate something called the ion product. This is analogous to the reaction quotient when we were talking about the equilibrium constant. So the ion product is analogous to the reaction quotient. Now, the IP, the ion product, is calculated using the same formula as KSP. And the utility of the ion product really lies in comparing its value to KSP. Each salt has a distinct KSP at a given temperature. And so by comparing the ion product to KSP, we can determine whether the solution is unsaturated, saturated, or supersaturated. So if the ion product is less than the KSP, then the solution is unsaturated and more solute can dissolve. If the ion product is equal to KSP, then the solution is saturated and at equilibrium. And last, if the ion product is greater than the KSP, then the solution is supersaturated and precipitation will occur. Now that's a lot of content we just covered. Let's go ahead and jump into some example problems. Now this first example problem, we're going to be focusing on concepts over math. And then in the later example problems we're going to tackle, we'll talk about math tips and tricks so that we can solve the problem without a calculator. This first problem says the molar solubility of iron 3 hydroxide in an aqueous solution was determined to be 4 times 10 to the minus 10 moles per liter. What is the value of the KSP for iron 3 hydroxide at the same temperature and pressure? So our ultimate goal is to calculate the KSP for iron 3 hydroxide. The first step then is to write the balanced dissociation reaction for iron 3 hydroxide. Iron 3 hydroxide dissociates into iron 3 plus and 3 hydroxide anions. Now with this balanced dissociation reaction, we can go ahead and write the KSP expression, keeping in mind that this is equal to the concentration of the product raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. Also, remember that we exclude solids and liquids from this expression, so iron 3 hydroxide will actually not be included since it is a solid. The KSP is then equal to the concentration of iron 3 plus raised to its stoichiometric coefficient multiplied by the concentration of hydroxide raised to its stoichiometric coefficient. Now with this, we want to figure out how to express these concentrations to ultimately calculate KSP. So the next thing we want to do is we want to set up an ICE table to figure out the initial concentrations of these ions, the change in concentration, and then finally the equilibrium concentration. And we're focusing on just iron 3 plus and hydroxide. Now, iron 3 hydroxide, this is a sparingly soluble salt. So initially, the concentration of these ions should be 0. Then over time, iron 3 hydroxide dissolves. It's going to dissociate to produce iron 3 plus and hydroxide ions. And we're going to represent that change with the variable x. Now, you might be quick to say that the change is going to be plus x for iron 3 plus and plus x for hydroxide, but that is incorrect. You want to be cautious of the mole-to-mole ratio between these ions and then demonstrate that appropriately with your variable. So the ratio here is 1 to 3. There's 1 iron 3 plus for every 3 hydroxide ions. So when we're writing the change, it's going to be plus x for iron 3 plus and plus 3x for hydroxide ions. And that means that the equilibrium concentrations for iron 3 plus is going to be x, and for hydroxide, it's going to be 3x. So now we can go ahead and rewrite our KSP to equal x multiplied by 3x to the third power. So we just replace this iron 3 plus with x and this hydroxide with 3x. And now this is our KSP expression. Now the following question is, well, do we know what x is so we can calculate KSP? And the answer to that is yes, we do. It's given to us in the question stem. The molar solubility of iron 3 hydroxide in an aqueous solution was determined to be 4 times 10 to the minus 10 moles per liter. This value, this molar solubility, is telling you what your x variable is. So then all we have to do is plug that variable in, that number in. 4 times 10 to the minus 10 multiplied by 3 times 4 times 10 to the minus 10 raised to the third power. And if you plug this into a calculator, you're going to get a value of around 6.9 times 10 to the minus 37. So that is the value for our KSP for iron 3 hydroxide. Beautiful. Let's move on to the second example problem. This example asks, what are the concentrations of each of the ions in a saturated solution of copper 1 bromide, given that the KSP is 6.27 times 10 to the minus 9 at 25 degrees Celsius. If 3 grams of copper 1 bromide are dissolved in water to make 1 liter of solution at 25 degrees Celsius, would the solution be saturated, unsaturated, or supersaturated. So we're asked two questions here. Let's focus on that first one where we want to figure out the concentrations of each of the ions in our copper 1 bromide solution. Now, to answer that, we're going to go ahead and again set up a balanced dissociation reaction for copper 1 bromide. This is going to dissociate into copper cations and bromide anions. Now, looking at this, we could also go ahead and set up our KSP expression. It's going to be the concentration of copper plus raised to its stoichiometric coefficient multiplied by the concentration of bromide anions raised to its stoichiometric coefficient. Remember that copper 1 bromide here is not going to be included because it's a solid, and we do not include solids and liquids in our equilibrium constant expressions. Now, we do know the KSP value. It's given to us in the problem. This is equal to 6.27 times 10 to the minus 9. Now, to figure out what we want to do with these concentrations so that we are able to calculate this problem, we want to again set up an ICE table focusing on copper plus and bromide anions. Now again, copper 1 bromide, this is a sparingly soluble salt, so the initial concentration for the ions should be 0. Now, over time, copper 1 bromide dissolves, it dissociates into copper cations and bromide anions. Now we're going to note that change using the variable x, and here the mole-to-mole ratio between these two ions is 1:1, so we're going to note plus x for both ions, and that means that the equilibrium concentration for both ions is also going to be x. That means that we can write the following expression: 6.27 times 10 to the minus 9 is equal to x multiplied by x, that's equal to x squared. Now here we want to be a little clever with our approximations so that it's easy to calculate the square root of both of these sides and get our value for x. In order to do that, I'm going to do two things. First, I'm going to move this decimal one place to the right. This gives me 62.7, and to account for that change, this minus 9 becomes a minus 10. Now, the reason I did that is because when we take the square root of both sides, doing the square root of 10 to the minus 10 just means that we're going to be dividing this minus 10 by 2, and that's going to give us a whole number as opposed to doing that with the 9. Now, the second thing I want to do is approximate this 62.7 to a number that's a perfect square, so to 64, because 8 squared gives us 64. So now we have 64 times 10 to the minus 10 is equal to x squared, and then we could take the square root of both sides to get our value for x. X is going to equal 8 times 10 to the minus 5. Now that we know our value for x, we can go ahead and figure out the concentration of each of these ions. The copper plus concentrations equal to x, and x is equal to 8 times 10 to the minus 5. So this is our concentration for the copper cations. Same goes for the bromide anions. Its concentrations equal to x, and we just said that x is equal to 8 times 10 to the minus 5. So there we have it. We answered that first question. Now the second question says, if 3 grams of copper 1 bromide are dissolved in a water to make a 1 liter solution at 25 degrees Celsius, would the solution be saturated, unsaturated, or supersaturated? To answer this second part, we need to calculate the molarity of the solution and then compare that value to 8 times 10 to the minus 5, since this is our molar solubility for copper 1 bromide. If our molarity is less than this value, then the reaction is unsaturated. If it's equal to this value, it's saturated, and if it's greater than this value, then it's supersaturated. Now, molarity is moles divided by liters, but we're not given moles of copper 1 bromide, we're given grams of copper 1 bromide. So we want to go ahead and convert this to moles using molar mass. The molar mass is 143.3 grams per 1 mole. We're going to go ahead and approximate the 143 to 150. And this is actually an easy calculation to do if we just write it in a different way. Let's write 150 as 1.5 times 10 to the power 2. Then what we can do is do this division first. 3 over 1.5 is 2. And then this is essentially 1 over 10 to the power 2, which is equal to 10 minus 2. So the number of moles of copper 1 bromide is 2 times 10 to the minus 2 power. Now we could take that and divide it by our volume, which is 1 liter, to get our molarity of 2 times 10 to the minus 2. Now we can compare this value to this value, and what we notice is the molarity of our solution is greater than the molar solubility of copper 1 bromide. And that means that this solution is super saturated. And that's how we answer this problem. Now we want to move on to the last topic of Objective 3, and that is the common ion effect. The common ion effect is a principle in chemistry that describes how the solubility of a compound is reduced when one of its ions is already present in the solution. This effect is a direct consequence of Le Chatelier's principle, which states that a system at equilibrium will adjust to counteract any change that's imposed on it. So let's consider the example of magnesium phosphate. All right, let's take magnesium phosphate dissociating in water. The dissolution of magnesium phosphate can be represented by the following equilibrium equation. Magnesium phosphate dissociates into 3 magnesium cations plus 2 phosphate anions. Now, when this salt dissolves in water, it dissociates into magnesium ions and phosphate ions, and that means that we can write the solubility product constant to be equal to the concentration of the magnesium cations raised to its stoichiometric coefficient of 3 multiplied by the concentration of phosphate anions raised to its stoichiometric coefficient of 2. If we now add a solution that contains one of these ions already present, such as magnesium chloride, then the concentration of magnesium ions in the solution increases. And according to Le Chatelier's principle, the system will try to counteract this change by shifting the equilibrium to the left, favoring the formation of solid magnesium phosphate. Now, this results in the precipitation of more magnesium phosphate and a decrease in the solubility of magnesium phosphate in the solution. Now, the common ion effect is really important in various chemical applications, like in precipitation reactions. It helps predict the formation of precipitates when mixing solutions. It's also important in buffer solutions. It explains the stabilization of pH in buffer solutions where a weak acid or base and its salt are present. And it's also important in analytical chemistry. It's used in techniques to control ion concentrations and manipulate solubility during titrations and other analytical procedures. Now keep this in mind, and let's go ahead and tackle an example problem together. This example says the KSP of silver iodide in aqueous solution is 8.5 times 10 to the minus 17 power. If 1 times 10 to the minus 5 molar solution of silver nitrate is saturated with silver iodide, what will be the final concentration of the iodide ions? So let's go ahead and focus in on silver iodide. This is a sparingly soluble salt. Let's go ahead and write the balanced dissociation reaction for silver iodide. This will dissociate into silver cations and iodide anions. From here, we can go ahead and also write the KSP expression for this reaction. This is going to equal the concentration of the silver cations raised to their stoichiometric coefficient multiplied by the concentration of the iodide anions raised to their stoichiometric coefficient. And we actually know the KSP value for this reaction. It's given to us in the problem. It's equal to 8.5 times 10 to the minus 17. Now, from here, we want to go ahead and set up our ice table because this is going to help us visualize the initial concentrations of these ions, the change, and then finally the equilibrium concentration that we can then use to plug back into our KSP expression and solve for the concentration of iodide ions. Now, this is where it becomes really important to take our ice table nice and slow. When we're just dealing with silver iodide, our sparingly soluble salt, the initial concentration of the ions is 0. But in this solution, we have another thing to worry about. We have silver nitrate. This is a soluble salt. It is found in its dissociated form in solution. That means initially we actually already have a concentration for our silver cations, and that concentration is equal to the concentration of silver nitrate we have, which is 1 times 10 to the minus 5. Our initial concentration for silver cations is 1 times 10 to the minus 5. Now our concentration for iodide is 0. Then what about the change? We're going to note our change using the variable x. And here we have a 1-to-1 ratio between the ions. So our change in concentration for silver is going to be plus x, and for iodide also going to be plus x. Our equilibrium concentration then for silver cations is 1 times 10 to the minus 5 plus x, and for iodide it's just plus x. Now we can take these and plug them back into our KSP expression. 8.5 times 10 to the minus 17 is equal to 1 times 10 to the minus 5 plus x multiplied by x. Now here, we're going to use our 5% approximation rule. We've discussed this in previous chapters to go ahead and say that x is small enough that it is negligible here, and this can just be 1 times 10 to the minus 5 multiplied by x. Now for the MCAT, you can usually make this assumption because they don't give you calculators, and you need calculators to do the quadratic formula, which is what you would have to do if we kept this plus x variable right here. So for the MCAT, you can generally omit this. Say that the 5% approximation rule applies here, and we can simplify our calculation. Now, when we do that, we now have 8.5 times 10 to the minus 17 is equal to 1 times 10 to the minus 5 multiplied by x. Now, what we can do is divide both sides by 1 times 10 to the minus 5. All right, and when we do that, we can now solve for x. Now, this is a really easy calculation. All right, this is going to be, you're going to maintain your 8.5. You're essentially doing 10 to the power of minus 17 divided by 10 to the minus 5. So this is going to be minus 17 minus 5, which is equal to minus 17 plus 5. That gives you minus 12. So the answer is going to be that x is equal to 8.5 times 10 to the minus 12. So this gives us x, all right? And this question asks for the concentration of iodide, which based on the equilibrium expression is going to be equal to x. So our iodide concentration is equal to x, and we know that x is equal to 8.5 times 10 to the minus 12. And there we have it. We solved this problem. Now we've completed objective 3. We can move into our last and final objective, which focuses on colligative properties. Colligative properties are physical properties of solutions that depend on the number of solute particles in a given amount of solvent and not on the nature of the solute particles. Now, these properties arise because solute particles interfere with the interactions between solvent molecules. Now, the key colligative properties that we're going to be discussing include vapor pressure lowering, freezing point depression, boiling point elevation, and osmotic pressure. Let's go ahead and get started with vapor pressure lowering. Raoult's law describes the vapor pressure lowering of a solvent when a non-volatile solute is dissolved in it. Now, according to Raoult's law, the vapor pressure of the solvent in a solution is directly proportional to the mole fraction of the solvent. Now, Raoult's law implies that the addition of a solute reduces the vapor pressure of the solvent because the solute particles occupy some of the surface area, reducing the number of solute molecules that can escape into the vapor phase. So for example, consider compound A in this figure right here. Now for compound A, in its pure form, so the mole fraction of 1, it's going to have a particular vapor pressure that's indicated here as Pa0. Now at the same temperature, compound B has a lower vapor pressure. You can see that right there. Now, as the concentration of B increases, the vapor pressure of A decreases. Indeed, as more solute is dissolved into the solvent, so as more B is dissolved into A, the vapor pressure of the solvent decreases. Now, this lowering of vapor pressure, it has significant effects on the other colligative properties as well, like boiling point elevation and freezing point depression. And that leads us into talking about those two. Now, boiling point elevation occurs when a non-volatile solute is added to a solvent, raising the boiling point of the solution relative to that of the pure solvent. Now, this happens because the presence of solute particles lowers the solvent's vapor pressure, requiring a higher temperature to reach the vapor pressure that's necessary for boiling. The boiling point elevation can be calculated using this equation right here, where delta TB is the increase in boiling point, I is the Van Hoff factor, Kb, this is the proportionality constant that's characteristic of a particular solvent. This is going to be provided on test day, and M is molality. Now, the Van Hoff factor, this I, corresponds to the number of particles into which a compound dissociates in solution. So, for example, for sodium chloride, NaCl, the I would be equal to 2 because each formula unit of sodium chloride dissociates into 2 particles, a sodium ion and a chloride ion when it dissolves. So that's boiling point elevation. What about freezing point depression? Freezing point depression occurs when a non-volatile solute is added to a solvent, lowering the freezing point of the solution relative to that of the pure solvent. Now, this happens because the solute particles interfere with the formation of the solid structure of the solvent, requiring a lower temperature to achieve the phase transition. Now, the freezing point temperature, that can be calculated, the freezing point depression can be calculated using this equation, where delta TF is the freezing point depression, I is the Van Hoff factor, Kf is the proportionality constant characteristic of a particular solvent, and M is the molality of the solution. Now, the last colligative property we want to talk about is osmotic pressure. This is the pressure that's required to prevent the free flow of solvent molecules through a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. Now, osmosis occurs because solvent molecules naturally move to equalize solute concentrations on both sides of the membrane. The osmotic pressure of a solution, it can be calculated using this equation right here, where T is temperature, R is our ideal gas constant, M is molarity, and I is the Van Hoff factor. Now, osmotic pressure is particularly important in biological systems where it actually helps regulate the flow of water and nutrients in and out of cells. Now that we've covered all 4 of the colligative properties, let's go ahead and hop into a couple of example problems. This first example asks, what is the vapor pressure at room temperature of a mixture containing 58 grams of butane and 172 grams of hexane? Note that the vapor pressure of pure butane and pure hexane are 172 kilopascals and 17.6 kilopascals, respectively, at 25 degrees Celsius. Now, to calculate the vapor pressure of each component, let's start with butane. We're going to need to multiply the mole fraction of butane with the vapor pressure of pure butane. And for hexane, we're going to need to multiply the mole fraction of hexane with the vapor pressure of pure hexane. Now we have the vapor pressure for pure butane and hexane, but we need to calculate the mole fraction for butane and hexane. We're given the mass of each. Let's go ahead and convert that to moles. So for butane, we have 58 grams of butane. Using the molar mass, we can convert to moles. Now, the molar mass of butane is 58 grams per 1 mole. And so this is an easy calculation. 58 divided by 58 is just 1. We have 1 mole of butane. Now, what about hexane? We're told that we have 172 grams of hexane, and the molar mass of hexane is 86 grams per 1 mole. 172 divided by 86, that's equal to 2 moles. Now, the mole fraction is calculated as the mole of the component divided by the total number of moles. The total number of moles is 1 plus 2. That's equal to 3. So the mole fraction for butane is going to be 1 over 3, which is approximately equal to 0.33. For hexane, that's going to be 2 over 3, and that's approximately equal to 0.66. Now we can start to plug things in back into our expression so that we can calculate the vapor pressure of butane and hexane. Now, for butane, we're going to multiply the mole fraction, 1 over 3, by the vapor pressure of pure butane, which is 172 kilopascals. Now, we can round this to 180, and that's going to be an easy calculation. 180 divided by 3 is 60 kilopascals. Now, for hexane, the mole fraction of hexane is 2 over 3, and we're going to multiply that by the vapor pressure of pure hexane, which is 17.6 kilopascals. Now we can go ahead and round this to 18. Then we have 2 over 3 multiplied by 18, and that's going to give us 12 kilopascals. All right, now the total vapor pressure is going to be the sum of the 2 vapor pressures here. So the total vapor pressure is going to be 60 plus 12, and that's equal to 72 kilopascals. And there we have it. We've solved this problem. Let's go ahead and jump into the next example problem. This example asks 400 grams of aluminum chloride is dissolved in 1.5 liters of water at room temperature. We're given the Kb value. How much does the boiling point increase after adding the aluminum chloride? Now, our expression for boiling point elevation is delta TB, this is the increase in boiling point, is equal to I, the Van Hoff factor, multiplied by Kb, which is our proportionality constant that we're given, multiplied by M, which is molality. Now let's go ahead and first figure out our molality. Molality is moles divided by kilogram of solvent, moles of solute divided by kilograms of solvent. Let's go ahead and figure out the numerator and the denominator here. Let's work through this logically. Water at room temperature, this has a density of 1 gram per milliliter. Therefore, 1.5 liter is actually the same as 1.5 kilogram. So that's our kilogram of solvent that's going to be in the denominator. Now, let's go ahead and figure out the moles of aluminum chloride. We know we have 400 grams of aluminum chloride. We can go ahead and convert this to moles by using the molar mass. 133.5 grams of aluminum chloride is equal to 1 mole of aluminum chloride, and 400 divided by 133 is about 3, so we have about 3 moles of aluminum chloride. Then molality is just 3 moles divided by 1.5 kilograms, and that gives us 2 molality. Wonderful, so that is M. Kb is given to us. What about I? I is the Van Hoff factor. This corresponds to the number of particles into which a compound dissociates in solution. Aluminum chloride, the I is going to be equal to 4 because it breaks down to form 1 aluminum cation and 3 chloride anions. Now, with that knowledge, we can start to plug things into our expression. Delta TB is equal to I, which is 4, multiplied by KB, which is equal to 0.512 Kelvin times kilograms over mole, multiplied by molality, 2. And when we carry out this calculation, 4 times 0.5 approximately, that's equal to 2, and 2 multiplied by 2 is equal to 4. So our increase in boiling point is going to be equal to 4 Kelvin. Wonderful. Let's do our last and final example problem for this chapter. This last example says 400 grams of aluminum chloride is dissolved in 1.5 liters of water at room temperature. And here we're given the Kf value. What is the new freezing point of this solution? Now, to calculate the freezing point depression, that's going to be equal to I multiplied by Kf multiplied by molality. Now, not much has changed from the previous problem. I is still equal to 4 because we're dealing with aluminum chloride, and the molality is equal to 2 because we have 400 grams of aluminum chloride dissolved in 1.5 liters, exactly the same as the previous problem. So then all we have to do is plug it into this equation. I is 4. We're given Kf, it's equal to 1.86 Kelvin times kilogram over mole. All right, and then that is multiplied by molality, which is equal to 2. Now, I'm going to approximate this to 2. 4 times 2 is 8, and 8 times 2 is equal to 16. So delta TF is equal to 16 Kelvin. That's our freezing point depression. Now, we're asked what is the new freezing point of this solution. Now, we're dealing with a solution that has water. The normal freezing point of water is 273 Kelvin. The freezing point is going to be depressed or decreased by 16 Kelvin. So what we're doing here is 273 minus 16. That gives us 257 Kelvin. Or in other words, if you want to convert this to Celsius, that's going to be equal to minus 15 degrees Celsius. And that's how we solve this problem. And with that, we've completed our chapter for solutions. We have worked through all of the objectives. We've done a bunch of practice problems. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.